Hello, everyone. My name is Andres Rodriguez, and this is my partner, Nicolas Prosperi. Today, we will be presenting our IE 311 final project, which focuses on an economic break-even analysis, comparing conventional sand casting and 3D printed sand molds. Our objective was to understand not only the cost differences, but also how geometry, tooling, throughput, and manufacturing readiness influence which process is better for a given production scenario. Here's the roadmap for our presentation. We'll begin with a process overview of both manufacturing methods, then we'll compare the major cost drivers, followed by a look at lead times and tooling. Next, we'll examine the geometric capability and then walk through the break-even analysis. We'll also review the advantages and limitations of 3D printed molds, discuss manufacturing readiness levels, and finish with our final recommendations. So meet the team. As mentioned, we're both industrial engineering students. This project allowed us to apply concepts from cost analysis, manufacturing processes, and productivity to a real-world decision engineers face when choosing between traditional and emerging manufacturing technologies. So for process overview, to begin, here's a quick overview of how each process works. Conventional sand casting relies on physical tooling. A wooden or metal pattern is made, sand is packed around it, and cores are created separately for internal features. The tooling creation process can take weeks and must be redone for design modifications. Now, for 3D printed sand molds, which is shown on the bottom right, eliminate the need for physical patterns, and instead, a CAD model is printed directly into a sand mold using binder jetting. This allows complex internal shapes and fast design iterations since no physical tooling must be fabricated or modified. Conventional casting has four major cost drivers. Number one would be the high tooling costs. Patterns and core boxes require significant upfront investment, making low volume production expensive. Number two is the long lead times. Tooling creation can take weeks, which would delay production, start, and slowing down any design change. Number three is the labor-intensive processes. Mold making and core handling are manual and introduce variability. And lastly, low cost of volume. Once tooling exists and each mold becomes very cheap, making it economical for large volume production. In contrast, 3D printed molds shift where the costs occur. Number one, hypermold cost. Each printed mold is significantly more expensive due to binder, machine time, and post-processing. Number two is the limited throughput. Printers can only output so much volume per hour, creating bottlenecks for large orders. Number three, digital workflow requirements. Strong CAD preparation and operator skill are necessary for this process. And lastly, the zero tooling costs. This is a major advantage. No patterns or core boxes are required, which drastically reduces costs for short runs and frequent design changes. This slide shows the contrast very clearly. Conventional casting requires 3,000 to over 50,000 in tooling, depending on part complexity, of course. Tooling modification also adds an extra cost and weeks of delay. While on the other hand, 3D printed molds, tooling cost is effectively zero. Design changes can be made instantly in CAD, and molds can be delivered in from 24 to 72 hours. This makes 3D printing extremely attractive for prototyping, which means that there's a low volume production and any application where design changes are expected. Geometry is one of the biggest differentiations between the two methods. Traditional sand casting is limited by parting lines, draft angles, and the need for cores. Undercuts or complex internal channels often require expensive tooling or simply cannot be produced. On the other hand, 3D printed molds allow organic shapes, lattice structures, undercuts, and fully integrated internal passages without using the cores. This reduces assembly, reduces machining, and allows the design that are impossible or highly expensive with conventional casting. Then is the break-even concept. This is the introduction. Economically, the decision between the two depends heavily on the break-even point. Conventional casting has a high upfront tooling cost, but low cost per unit once production begins. 3D printed molds have no tooling costs, but each mold is comparatively expensive. So the break-even point depends on the number of units, the tooling complexity, and the required precision and finishing needs.
So, based on industry data and the cost relationships shown earlier, the break-even point usually falls between 50 and 200 units. For 3D printing is favored when tooling is very complex or expensive and there's a frequent design iterations are required. Now, for conventional casting, it is favored when the part is simple, the geometry works with standard tooling, and the expected production volume is high. So here are the key advantages of 3D printed molds. No tooling or pattern storage required. It is ideal for low volume or custom production. It supports extremely complex geometry. It designs changes can be made instantly. It reduces scrap and rework for complex casting. And lastly, overall much faster time to market. Disadvantages becomes especially impactful for research and development environments and industries with rapidly changing designs. However, conventional casting has several limitations, including number one, high tooling dependence. Every design needs its own pattern and core box. Number two, geometric limitation. Undercuts and complex channels are hard to achieve. Number three, long lead times. Tooling fabrication takes weeks, even months. Number four, high labor involvement, increasing variability and risk error. These limitations are exactly what 3D printing helps overcome. 3D printing also has its drawbacks. It is very high per mold cost at volume. It slows production rate due to printer build time. The surface finish often requires more machining and limited machine availability and specialized material requirements. So while 3D printing molds are extremely flexible, they are not the best fit for high volume manufacturing. So this slide summarizes the ideal use cases. For 3D printing molds work best for 1 to 200 units per year when there is a complex or conformal geometry, when research and development, prototypes and aftermarket parts, and if the programs with frequent design changes. And for conventional casting works best for 300 plus units per year, simple and stable geometry, long-term repeatable production, and tight dimensional consistency requirements. For readiness standpoint, conventional casting is at a manufacturing readiness level of 10, meaning it's fully mature with stable supply chains, predictable quality, and high repeatability. For 3D printed molds, the manufacturing readiness level is around 7 and 8, meaning they're production relevant but not yet optimized for high volume manufacturing. Machine availability, binder materials, and workforce training still limit broader adoption. So, some final recommendations based on the technical, economic, and readiness factors we analyzed are number one, use 3D printed molds for low volume, complex geometry, or rapid iterations. Number two, use conventional casting for high volumes and stable production. Number three, consider hybrid approaches such as 3D printing cores inside conventional molds. Number four, adopt 3D printing early in the development cycle to reduce tooling risk. And number five, maintain conventional molding capability for high volume programs. Thank you for listening.
Thank you.